Welcome back. Last time we talked about impossible differential cryptanalysis, so we look at the theory behind it, but now it is a good time to see an example on a block cipher. So for this example I chose the block cipher Hight because it's the generalized face-down network, and impossible differential attacks are really powerful, this kind of ciphers. So Hight is actually a lightweight block cipher designed by Hong et al. It was first published in Chess 2006. It is shown to be highly convenient for extremely constrained devices. RFID tags and sensor networks became a standard encryption algorithm in South Korea. So these are actually one of the first lightweight ciphers that we know in the literature. It is a generalized unbalanced face-down network. Actually, Hight is also an ISO standard for block ciphers, but it failed to become an ISO standard for the lightweight block ciphers, let's say. So for the specifications of the cipher, the block size is 64 bits, key size is 128 bits, and number of runs are 32. So in the original paper they said they provided this comparison, and they showed that they can implement Hight with less number of gates than AES. Of course, there are a lot better implementations of AES that requires less gates, gate equivalents, let's say. And in the paper they showed that their throughput is way better than AES. Of course, later on, different studies reduced the number of gate equivalents required to implement Hight, but of course, if you perform such an implementation, the throughput would not be as high as 150 megabits per second. And many studies have been done in the literature, but of course these are before the NIST lightweight standardization process. So this Hight was one of the early examples, but now we have many lightweight designs, and we have a lot better ciphers which provide better throughput, less gates, gate equivalents, and better security in terms of number of attack runs. So before giving the example, the impossible differential attack, let's look at the notation that we are going to use in this work. So you know that this is the symbol for XOR. In this analysis we will use this kind of addition symbol for addition modulo 2 to the 8. So we will be adding actual bytes to each other, but so it would be addition modulo 2 to the 8. This is used for left rotation of I bits. When we talk about R rounds of Hight, we use this notation. E sub j is the notation for a byte with zeros in all positions except the bit j. So a byte has 8 bits, so we start counting them from the rightmost bits, so we start from 0 to 7. So E0 means that the rightmost bits is 1 and the remaining ones are 7. So if you also see a tilde, this means that a byte that has zeros in bits 0 to j minus 1, but then a 1 bit in the j position, and the remaining bits are indeterminate, so they can be either 0 or 1. We will be using the question mark to represent this kind of bits. So if you also see a bar at the top of j, this means that all of the bits from the 0th position to jth position are 0, but the remaining ones, starting from j plus 1 to 7, are indeterminate. And for bytes we will use the question mark to represent that all bits of the byte can be anything. Since Hight has 128 bits of secret key, it is represented by 16 bytes denoted as MKI. In the beginning and at the end of the encryption operation, there are whitening keys. They are represented by WKI, and inside the round we will be using subkeys, and we will use the notation SK sub I. So let's give some examples for this E notation to understand what is going on. We are going to need this because this cipher both uses XOR operation and addition, modular addition. So we have to see how differences in terms of XORs are propagated through addition. This is why we need such a notation. So I already given some examples, but let's look at E3 tilde. This means that 0, 1 and second bits are 0. Third bit, as not represented here, is 1, and the remaining bits are question mark. That can be anything. And if you have a bar at the top of this bit, it means that it is also 0, and remaining bits can be anything. But with a question mark for a byte, we will be representing that all of the 8 bits can be anything. So let's look at the structure of the Hight block cipher. So we have the master key, and from this master key, using the key schedule algorithm, we will be generating whitening keys. All of the terms here are bytes, so there are 8 bytes here, sorry, 4 bytes here and 4 bytes here and so on. So we will be generating whitening keys, sub keys, and then whitening keys again. So there is an initial transformation, which is just addition of these whitening keys, and there's a final transformation, which is again just addition of these whitening keys. In the attacks that we are going to do, we will be omitting this initial transformation because we were trying to improve the attacks in the literature, and the attacks in the literature didn't use this initial transformation, but we kept the final transformation because it doesn't affect the performance of our attack. So as you can see, there are 32 rounds for the cipher. So you might think that since we are going to attack the master key, but since we can capture only the whitening keys and sub keys here, what is the relation between these whitening keys, sub keys, and the master key? You need to check the key schedule for that, but Hight has a very simple key schedule. So instead of giving the key schedule, we provided a table that shows the relation between the original key and the whitening keys and sub keys. For instance, in this table, this means that if you know the first byte of the secret key, which we denote by MK0, this means that you already know whitening key for sub key 0, 17, 34, 51, and so on. So, but one can be obtained from another. So this also means that if you just know SK17, then you know everything in this row. Okay, so this actually makes the attack easier. For instance, in order to perform the attack, if you need the value of SK0 when you guess it, this means that you already guess MK0. This means that you get the SK17, SK34, or whitening Q4 as a bonus without paying anything for that. So this kind of weak schedules actually provides a good performance, but also it helps the cryptanalysis a lot to break the cipher. So we will be using all of these relations in our attack. So let's look at the cipher. This is the one round of Hight. So we thought that the block size is 64 bits. So there are 8 lines here. So this means that all of the lines in this picture represent a byte. So you divide the plain text into 8 bytes. We again start counting from rightmost part to the left as we start counting from 0. So this is how we represent the bytes. As you can see, instead of a single phase-style network, we have a generalized phase-style network. So it is like 4 phase-style networks concatenated together. As you can see, there are some parts where you have the XOR operation and some places where you have the modular addition. Sometimes they are replaced, as you can see. So this is why we need to check how differences propagate through these operations. So of course in this picture what we also need to know is the definitions of the functions f0 and f1. You might think that there are many things going inside this function, but actually they are very simple functions. For instance, when a byte comes to this f0 as an input, this byte x is actually rotated 1 bit, 2 bit, and 7 bits, and they are XORed to each other, and the output is produced here. So it is just a simple rotation operation and two XOR operations. So as you can see, this f0 and f1 functions are really simple. And this might be surprising to some of you because so far all of the block ciphers we have seen contained S boxes as for their substitution layer. And as you can see, these rotations can be seen as the linear layer, and you might think that then where is the confusion comes from because this cipher doesn't have any substitution layer. Actually, it comes from this modular additions. Since you are mixing the modular addition with the XOR operation, so if you have differences in terms of XORs, then those differences would behave differently after this modular addition or this addition. So the nonlinear operation in this cipher comes from modular addition. As you can see, this is a very simple design. This is why we call it actually a lightweight design. But for impossible differential kind of attacks or for truncated differential attacks, this kind of many lines, which is a generalized face-down network, actually helps the attacker to find very long differentials. For this reason, actually, the cipher is 32 rounds. If it were, if it had less rounds, maybe like 20, we could practically break this cipher. So you might think that what kind of differentials I can find for this kind of stuff. Recall that the face-down network means that you are modifying half of the cipher in a round. For instance, let's look at here. This byte comes here. It's performs some operations, and so the output changes, and it actually modifies this byte. So this byte is changed, but this byte comes and goes here. So half of the bytes are not affected during a single run. So for this reason, for face-down ciphers, we actually get a one round free for when we are searching for differentials. For instance, assume that these bytes has no differences. So assume that we are trying to perform a differential kind of attack. So these bytes are all the same for our input pair. But for this byte, we have some difference. This difference comes here, but there is no difference here. So the zero difference goes here. So there are no differences here, and zero is XORed to here. So this difference comes here and goes there. Since all of them are zero, these parts will be zero as a difference. So you perform one round of encryption and it actually affects nothing in terms of differences. So question is, and in the next round, since you have a difference here, it will come here, it will come again here and goes here for the second round, but it will affect this part and it will affect this. So you will have 0, something, something, 0, 0, 0, 0, 0. But since we have a lot of branches, you might guess that we can go in this way and obtain like 5 or 6 rounds of truncated differentials with probability 1. So this is actually the basic idea. Now let's look at some properties. We know what an XOR operation is, and we know that XOR operation preserves differences of course if your differences are given in terms of XOR operation. That is, if A XOR B is C, then if you XOR A with some value and also B with the same value, then since the XOR operation will cancel these D's, you will still end up with C. So this is the thing we have been doing all this time in our lecture. Now the question is how this difference is affected by modular addition. So the modular addition operation preserves the first least significant zero differences. Others may not be preserved. So assume that A XOR B is C, but C has some zero differences at the rightmost bits, and there's 1 here, then beginning part are something else. So if you add A with D, but this time you are performing modular addition, and here again you are performing modular addition, their XOR means that these zeros, the differences of XOR zeros will be kept. This one is also be kept, but since there will be carry bits, we won't be able to guess what will be going on after this question mark. So this is why we invented this notation. Actually, the designers of the first attacks use this notation. So this means that EI tilde. So there are I minus 1 zeros, ith bit has 1 as a difference, and the other ones can be anything. So we will, this way we can see how the differences in terms of XOR are propagated after the modular addition operation. And we also observe something. If you put this input to F0, you end up with E7, and it is easy to see. I mean, go back to the definition of F0, since it is the rotation and XOR of X's. You can just easily check that if you put this as an input to F0, the output will be E7. And we also observe that if you put E7 to F0, you get E0 tilde. And if you do this for the F1, you get E2 tilde. Okay, but we will see in an exam soon why these are important. Okay, because in the next step, we will be trying to find the longest impossible differential that we can find for this cipher. So, this is how it works. So I already told that if you give the input difference here, it will go from here and here, so you will get something as a bonus. But actually this is what people did in the literature. The designers and Dan Liu provided an attack where they used this kind of technique, because this is intuitively the best approach, because you give the difference here, it doesn't affect any of the branches here, so it comes and goes here. So we said that maybe we can come up with something better. So we said that instead of giving difference here, let's say that we give difference to both of these bytes, but we choose them in a very specific way, so that this difference, when you put it into F0, end up with E7. And since E7 means that the difference is on the leftmost bit, the modular addition doesn't affect this difference, so it comes here. And since if you put E7 here, they cancel each other. So this one comes as a 0 and goes here. And this difference comes from here to here. So if you perform one round of encryption, this is what happens. This difference comes here and goes here, like this. This E7 is cancelled here, so it becomes 0 here. So now we gained one more round, because now in the second round of encryption we have differences as zeros here, but we have difference something else here, but it will come here and goes here. The remaining ones will be 0, as shown in here. So we have two rounds of encryption, but we have difference only in one of the bytes. This is a good thing, because now if you perform one more round of encryption, this difference will come and goes to here, and it will, after F1, it will turn into something and will become question mark here, as it's shown here. Let's do it one more time. Now the rightmost two bytes have the differences 0 and this, so 0 will come in here, 0 will come in here, so this thing will go here. But now you have question mark here, question mark goes here, and question mark becomes question mark again and goes here. So now you have two question marks, like here, and E0 tilde because of the modular addition, and so on. So if you continue in this way, you will, and actually you should take a pen and paper and observe that this is correct. Okay, this is a good exercise. If you follow these differences after 9 rounds of encryption, you will see that all of these 7 bytes becomes something, probably something non-zero, but we don't know what it is. But the important thing is that the leftmost difference here becomes E0 tilde. Recall that E0 tilde means the rightmost bit is 1, which is, we are talking about differences here, and the remaining 7 bits can be anything. So this is the longest path that we could find, and as far as I know in the literature, this is the best known. Now, if you recall our discussion of impossible differentials, we talk about miss-in-the-middle technique. So this is actually the beginning part of the miss-in-the-middle technique. So far what we have done is, we started with some input difference, and after 9 rounds of encryption with probability 1, we say that this bit has difference 1. So this is a probability 1 9 round of truncated differential. So let's go back to the picture of miss-in-the-middle technique and see what we are trying to do here. Recall that this was the idea in the miss-in-the-middle technique. So far we only done this part. we started with an input difference with probability 1. We said that after 9 rounds of encryption, the output difference should be in this form, where we only say that there should be a difference of 1 in 1 bit, and we actually don't know what happens in the remaining 63 bits. So this is the part we have done. Now we should do this part. So we should start with an output difference, go back in the decryption direction and obtain some difference, but it should not meet this one. They should miss. So the name of miss in the middle technique. So let's go back to our example. So we found this 9 round truncated differential. Now let's start something from the bottom and try to go up, and let's try to make it miss with this one. So here is an example that we found. We said that if we put this, if we choose this output difference 0 E7 0 0 0 0, so you have 0 here, E7 here. So if you go upwards now, E7 comes here and goes here. Since there's 0 here, this means that the input is 0, so this 0 should go there. So this is why when you go upwards, you have 0 0 E0 and so on. Now this means that we have 0 0 E7 here. So this means that if this is the output, the input must be, since you have E7 here, this should be E7, right? Because they has to be same. But you have 0 here, and this, if this is E7, it has to go this transformation, and there should be something, the output should be non-zero, but we already have 0 here. But we also say that if you put E7 to F1, it becomes E2 tilde, so you know that there's E2 tilde here, but 0 here, so this means that there should be E2 tilde so that they cancel each other. So this is why E2 tilde pops out here. So if you continue in this way, in the upwards direction, this E2 tilde turns into E0 tilde, and so on and so on. And at the end, what you observe is that before the final decryption, you have E7 here and E0 tilde here. So E0 tilde comes here to here, E7 comes to here and here, but E7 after F0 becomes E0 tilde. So if you XOR E0 tilde with E0 tilde, you end up with E0 bar tilde. So this means that this bit has to have the difference of 0. Now, if we combine both of them, this is the picture. So you started with this input difference, 9 rounds later, you ended up with this. You started with this output difference, 8 rounds in the decryption direction, you ended up with this, but they do not match. As you can see, this is E0, this is E0 bar. So here the bit difference is 1, here it is 0. They miss in the middle. So recall our picture in the miss in the middle technique. So they do not meet, they miss in the middle. So this means that this input difference has to go to this, and this output difference has to come from this. And since they are not the same, this input difference has to go something else. So this input difference after 17 rounds of encryption can never end up with this kind of output difference. So this is the impossible property that we observe. So, but as you can see, the cipher is 32 rounds and we found a 17 round impossible differential, which is actually a very good result. And the designers couldn't find something this long. So this was, as far as I know, the longest impossible differential in the literature. And we tried, but we couldn't come up with anything better. And so far, we couldn't see any way to come something longer than this. But of course, if you can find a property that you can exploit, maybe you can find something longer. So next thing we will do is to use this differential to perform the attack, but I'm leaving that to our next video.